Hi, everybody. Thanks for tuning in today. Happy Friday. This week's seminar speaker is Dr. Jessica Noviello, who is currently a postdoc at the NASA Goddard Space Flight Center. Dr. Noviello is a planetary scientist whose research is focused on characterizing the surface and interior structure of icy moons, asteroids, and Kuiper Belt objects, and more recently exoplanets. She received a BS in physics and a BA in Earth and Planetary Science from the Johns Hopkins University and a PhD in planetary geology from the Arizona State University. In 2019, after that, she did a postdoc at ASU until 2021, and then she started her current position at Goddard, where her research has focused on exoplanets with the Nexus network. But today we'll be hearing about her work with the dwarf planet Haumea. Thanks again for taking the time to talk with us, Dr. Noviello. Take it away. Thanks again.
Well, thank you so much for that fantastic introduction and of course for the invitation to be here at all. I'm really excited to give this talk today. I think it's a lot of fun, and this is a planetary body that people don't hear enough about, but I think it's one of the coolest little puzzles in the entire solar system. So let's get started, jump right into it. But what exactly about Haumea makes it such an interesting object? Well, the first time it was observed was in 2003. It was identified in 2004. Even how it was discovered is a bit of a controversy. Two different groups discovered it around the same time. So even when it was first discovered, it was already a very interesting kind of planetary problem, but for a slightly different reason. Right now it's classified as a dwarf planet because of its size, which means it's actually in the same class as other objects like Ceres in the asteroid belt and Pluto, which very sadly got demoted from full planet in 2006, I believe, or was it? Nope, 2006. So Haumea is currently orbiting at 43 AU. It's about 4 AU beyond Pluto right now. One of the other weird things about it is that there is very strong evidence that its surface is mostly water ice, and estimates are 90% and above. And a lot of that information comes from the spectral data that comes back that shows strong evidence of that water ice absorption lines. This is almost fully unique among Kuiper Belt objects, and it's actually an important part of how the Haumea family was discovered in the first place. There's also a mysterious red spot on Haumea, although we don't have the imaging resolution to determine, or the spectral resolution to determine exactly what it is. But it's a big question mark on the entire system, because could this red material actually be some kind of outwelling of maybe cryovolcanism or like cryo lava, or could it be something else that has a more astrobiological significance? So just a lot of weird things going on with Haumea. And if that weren't weird enough, it also has at least 2 moons and a ring system and about a dozen other objects kind of scattered around but dynamically associated with it. So already it's got this list of characteristics that is very unusual for a planetary body, especially something so distant from the sun. It was a relatively unexpected find. Let me flip back, and just to say that if you are somebody who has light sensitivity, or if you struggle with motion on videos, you might want to look away for this next screen, because it is a GIF of observations of Haumea itself. All right, so what we are showing, or what I am showing on the screen here is actual observations of Haumea taken by one of our co-investigators, Sarah Sonnet. You can actually see the big dot in the middle of these squares. That is Haumea, and if you look closely, especially in the one on the left, you can actually see its 2 moons moving around it, and that is Ha'iaka and Namaka. Namaka is actually the one that's more distant. So this is actual data. We are still actively observing Haumea, and a lot of the data that I will talk to you about today was taken in ways very similar to this and then analyzed by the co-I Sonnet. So here are some more specifics about Haumea, particularly its size and its density. It's about 1,050 kilometers long. It's actually it's quite a large object. Again, it's a dwarf planet, and what is also interesting about its shape is that it's a triaxial ellipsoid, so it's not very spherical at all, and yet it is rotating at an incredibly fast rotation rate, about 3.91 hours. This makes Haumea the fastest rotating large object in our solar system, and it's a big question of how exactly it got to that very fast rotation rate and what it means for the history of the entire system itself. And this ends up being a very important tool that we use to carry forward our research. We also know that its density is around 2 grams per centimeter cubed. That tells us that a large part of it is actually ice. That brings down the density from something more rock-like, like 2.7, or even higher, like 3.3, down to about 2. So a good fraction of it has to be ice. And we kind of knew that already just by looking at the surface spectral features. We do have a good estimate of its mass. Again, we get that from studying how the moons orbit around it. When we talk about modeling this, though, because it's not a spherical shape, we have to be a little clever about how we do it, but we still apply the principles of things like hydrostatic equilibrium to this rotating body. We just have to be slightly more clever about taking into account its triaxial ellipsoid shape and how that influences the internal differentiation of Haumea from start to present day. But I keep alluding to the fact that Haumea is not alone out there. Of course, it has its 2 moons, it has a ring system, and it also has a few other objects that are dynamically associated with it, but are not necessarily orbiting it. And a lot of these objects, when I say dynamically linked, I do mean that their orbits show some kind of pattern, so a very close association with the orbit of Haumea itself in terms of things like the inclination angles and their velocity distributions. So I am not a dynamicist. I can't speak exactly to this, but I do know from the reading and the work that I've done that a lot of these objects, there's no good explanation for how they exactly got their state unless they came from Haumea itself. And one of the other big pros for the argument that these objects came from Haumea, or at least are very closely associated with Haumea, is the fact that they too also show very strong evidence of that water-ice absorption. So we see this characteristic of water-ice and dynamical association, and we link it together, and we think that Haumea then is part, or is the largest member of the Haumean dynamical family. Dynamical families in terms of asteroids within the asteroid belt are actually pretty common. There are many known asteroid families, but in the Kuiper belt, it's really only Haumea. So the question then becomes, how did it make its family and where did they all come from? What this chart is actually showing is that there are so many different ideas that have a lot of pros and cons. Part of this research into figuring out what actually happened is just about getting more data about what these family members look like and more precise information about their orbits. So there are many different ideas. One thing they all have in common, though, is that at the beginning of Haumea's lifetime, as a little dwarf, well, I say little, as a pretty big dwarf planet, actually, it had to have been impacted pretty severely to give it that enough angular momentum to give it that very quick under 4-hour rotation period. And after that, it's, I don't want to say all bets are off because they do have to actually focus on what the data are saying, but there is a lot of opportunity for a new explanation to come in. So this is this question that we ended up solving in this work, or at least we put forward a plausible hypothesis of what actually might have happened. So just to recap before we launch into that explanation, Haumea is a big, differentiated, quickly spinning object covered in water ice. Previous work done by one of my friends and collaborators, Emily Dunham, actually tried to get at the structure of what Haumea's interior would have looked like and found that the ice mantle, if we assume that Haumea is broken down into core and mantle and we kind of just wave the crust of Haumea away for a little bit, we actually find that the mantle accounts for about 17% of the mass by volume, and that the core density ends up being more like a clay kind of density at 2.7 grams per centimeter cubed, rather than something that's more pure rock at 3 or 3.3 or even 3.7, which might be more of an iron core. So these are some of the charts that they made in their paper. These charts were made, well, they were made in MATLAB, but the data come from a specific code called Kyushu, which is a code that the PI of this grant, Steve Desch, has written. It's a Fortran code that is specifically designed to calculate the equilibrium of a rapidly rotating differentiated body, exactly like what Haumea is. So now that we've done all this, and now that we have this understanding of what Haumea is and what exactly is so weird about it, what do we do with it next? And how do we take all of this information and try to weave it together into a story that makes sense? So this is our explanation. We present this as more of a plausibility argument. We have not yet evaluated the probability of this statement, but just as a way of thinking about it, we combine geochemistry and geophysics into this explanation, and we think it explains a lot. So I hope you enjoy this. So first, in the very beginning of the solar system, Haumea is still forming out in the solar system. It's actually not even Haumea yet. It is this proto-Haumea that is just minding its own business in space when all of a sudden this gigantic, well, similarly sized but still pretty gigantic object comes and hits it at a relatively low speed. And it has to be a low speed because if it hit too high, proto-Haumea would have completely broken apart into a catastrophic disruption event. So it had to be somewhat slow relative to the speed of proto-Haumea itself, and it was probably more of an oblique impact. And we say this for one good reason that we'll get to on the next slide. But the point is, proto-Haumea was just minding its own business when it got whacked by another proto-Haumea, or at least something very similar sized. Now, the reason I say it has to be more of an oblique impact is because one of the things that we think happened at this point is that the cores of these two bodies, which were semi-differentiated at the time of the impact, the cores have actually started to merge after this point. So we are now creating this larger object that will eventually become Haumea. But at this particular moment of impact, first, these bodies have to lose a lot of material, and that material is lost to the system entirely. It does not reaggregate to form a ring. It is gone. So this material no longer contributes to any kind of information about the state that Haumea is currently in. So as the cores from these two objects now merge into one, differentiation needs to restart. So they were partially differentiated, or we think they had to have been at the time of the impact, but then once the impact happens, it's so severe that the clock resets and differentiation begins anew. So there's a lot more material. There's ice and rock that is mixed in together that does eventually start to differentiate. And at the same time, the core itself is growing. The moment of inertia of this system changes, and moment of inertia is actually one of these threads that we have to pay attention to as we walk through the different stages of evolution for Haumea. So at this point, material is starting to spin off, but it's not necessarily related to the impact event itself. It's something that just happens because Haumea starts to spin so incredibly quickly. It actually cannot hold on to all of its material. It's actually starting to fission off little parts of it. But I have used this word moment of inertia, and I think we should take a moment to remind ourselves what that is and what it means in a planetary context. So moment of inertia in planetary is often used as a shorthand way of describing how much the mass is distributed within a rotating body. And more often than not, it's a spherical rotating body. For a sphere, the moment of inertia is the I value is calculated as 2/5 mr squared, where m is the mass of the body and r is the radius of the sphere. Okay. I hope somebody got into the door. But anyway, because we have to consider that Haumea is not a sphere, it's actually a triaxial ellipsoid, the moment of inertia formula is actually slightly different. It's actually 1/5 m times a squared plus b squared, where a squared is the longest axis squared, b is that middle axis squared. This is what we use. We actually compared the sphere to the ellipsoid, and of course we ended up going with the ellipsoid, not just because it was a better approximation, but because it is a much more useful value, especially for something like Haumea. But to give you an idea of what this looks like in terms of planets, the Earth normalized moment of inertia, so that's the actual value of the so the 2/5 mr squared in real life divided by the pure mr squared. So it's a ratio, effectively, of how homogeneously that mass is distributed throughout the entire planet. On Earth, because Earth is very differentiated, we actually have a relatively low normalized moment of inertia, but the Moon, it turns out, is much more homogeneous, so that has a relatively high moment of inertia. It's almost exactly that 2/5 or 0.4 value. So we see it in a couple of different places. It's a relatively tricky value to constrain because it does require lots and lots of different orbits, or at least flybys. So of course we don't have that with Haumea, but it turns out we can estimate it just from information that we have, or will have, once we do the modeling. So back to what actually happened, what we think happened with Haumea. So as the core is growing, it's not just changing the moment of inertia, but it's also changing the spin period, which are linked by the angular momentum of the system, which is just moment of inertia times that angular spin rate. Because the spin rate is changing, the material on the edges actually starts flying off more and more excitedly. Specifically, it's coming off of the longest axis because that's where the gravity would be the least powerful. Eventually, we think this material, it hasn't been lost to the entire system. Eventually, we think that it recreates into the Haumeans and the ring that we observe today. But at the same time, the core is continuing to grow. And because the heat from differentiation is actually causing a lot of the ice to melt, all of that water is percolating into the core, where something very interesting happens. As the water goes down into the core, it actually, we think, would fully hydrate the core and lead to a mineralogical change via serpentinization. Again, the core is still increasing in size. We're still looking at how much the moment of inertia is changing as a result of this, but because it's starting to become an actual sizable portion of Haumea itself, it starts to decrease relatively. So this is a bit counterintuitive, but basically it gets so big that it starts to become more homogeneous again. So that part was a little wild to me to think about. But what is serpentinization? We do know that it happens not just on Earth, but we know that it happens in planetary bodies because we see evidence of it mostly in meteorites, which have that, specifically carbonaceous chondrites, which have a density close to what is observed on Haumea today, or at least estimated on Haumea. The clays, or these hydrated silicates, typically have densities between 2.6 and 2.9. Remember that from Emily Dunham's work that the Haumea's core has been estimated to have a density of about 2.7 grams per centimeter cubed, so maybe Haumea's core is actually hydrated clays. So the numbers are seeming to work out here, but as an example of what that would look like in terms of how significant some of these changes could be, we on Earth could start out with a mineral like peridotite, and through serpentinization, we actually end up with the rock serpentinite. So we're thinking something like this might have happened on Haumea to actively hydrate the core and bring the more rocky core to something that is more of a clay-like structure. So finally, after the geophysical and geochemical changes, the core has stopped growing, the rotation rate eventually slows down to its present value, Haumea's moons and rings stabilize, and the other objects also stabilize into their orbits, and we, as humans, get to observe it. So there was a lot that just happened. Let me go through it one last time just to remind you all of the different pieces that we're trying to tie together. First thing that happens is that Haumea gets hit by an object of similar size relatively slowly and obliquely. The two bodies merge together and differentiation re-begins, or just restarts. Haumea's core grows, and some of the material begins to spin off. Haumea's core then fully hydrates via serpentinization, and even more material spins off that eventually forms the moons and the rings that we observe. And finally, it stabilizes. The core stops growing. Haumea is observed by humans, and this is the story that we think happened. And now I have to I get to talk to you all about the evidence that supports this hypothesis. Because there's a big question of how do we truly determine if this happened? Because there's a lot of speculation going on here, and there's not a whole lot of data, especially because Haumea is, it is big, but it's very far away, so it is still difficult to observe. But one of the tools that we have, or at least one of the most critical values that we have, are estimates about its total angular momentum, and this ends up becoming a very important part of the story that ties everything together. But from our codes, we can also do things like estimate that c-axis, which can't be directly measured from observations. We can estimate its core density and also the density of the beginning of the mantle itself to determine how the physical structure of Haumea exists at its present day. And we can use this information to trace back, looking for values that keep things like angular momentum the same value as its modern day. We are making assumptions that there was no significant loss of mass after that first impact event, so that the angular momentum value would have stayed the same, but it's not a bad assumption, and it's one of the only pieces that we can really hold on to. So the first step that I did was try and figure out what Haumea could look like today, because if we know what it looks like today, or at least if we have a good constraint on what it could look like today in terms of what its geophysical structure is, then we can use that information to trace backwards in time. So I used the Kyushu code to explore the possible physical states of Haumea. I varied the a-axis because even though the observations are mostly in agreement, there is still a range and an error bar, and we just wanted to explore everything. So I varied a-axis, b-axis, and I looked at how those values affected the density and the output average density, the output core density, how it affected things like the c-axis as well, and core size. There are many, many different graphs, but here are the ones that I think are the most illustrative, because they show that how the density changes, and here we can start to get an intuition of what the core actually looks like. And the core graph is the one on the right, and you can actually see that most of the values for the core density, regardless of the size that I begin with in terms of the A and B axes, most of them actually have a density that suggests the core could be very clay-like. So that was already a very exciting and complementary discovery to the earlier work that Emily Dunham led. We also, of course, looked at the moments of inertia. We wanted to make sure that we understood what it was today so that we could track how it changed throughout time. Again, that C value is that normalized moment of inertia, and just going through and looking at how it changed as a function of the density of the mantle. The density of the mantle is just a fraction of how much ice versus rock is in the mantle. Of course, the ice we assume to be water ice. And I did here in these examples keep the A and B axes fixed at the values that Emily Dunham suggested in their earlier paper. So this again is just showing now the total angular momentum. Again, we're just trying to place modern constraints so that when we look back in the future or back into the past, we actually have an anchor point, something that we're looking for and useful values to tie us to the present. All right. Oh, perfect. I got ahead of myself because that's exactly what this slide says. So now that we have this baseline established by all the modern modeling, it's time to reach backwards in time. We know from other observations that the total mass of the known Haumean family is about 3% of the mass of Haumea itself. So if we were to go back in time, we would need to model a Haumea that is 3% bigger to account for the mass loss that happened during this proposed hypothesis. If Haumea lost 3% of its mass, especially along its long axes, it actually would have lost about 13% of its total angular momentum. And again, that mass would have to come out from the longest axis because that's where the gravity would be very close to zero or even negative. So just any kind of disturbance would have blown that material off very easily. So when I started modeling previous Haumea, or like very soon post-impact Haumea, I was looking for a 3% larger Haumea that had a 13% larger angular momentum, a very close to zero or negative gravity along the longest axis, a larger A-axis, a shorter rotational period, and a core density that was more rocky than clayey. Those of you who do modeling can probably guess what I'm going to say next, but this is the time for an exploration of the parameter space. So if you haven't seen the Marvel movie Infinity War, you might want to close your ears and shut your eyes for about a minute. But in the film, Doctor Strange looks through something like 14.5 billion combinations or permutations of events to try and figure out the one way to defeat Thanos. And he does find that one way eventually. But I'm just going to throw out there that I only had to do about 50 Kyushu runs, and it turns out I found two and a half solutions, two of which worked great. The other one was like, close enough. But like, I'm just saying, like, Doctor Strange, let's collaborate. I think we can solve more problems. All right, so these are the answers that I actually found. So varying A, B, and P being the period at that larger fixed mass that is about 3% larger than modern day Haumea, found two solutions that worked really well and one solution that we thought should be included, and that's the one with the asterisk in this column. So the three solutions here are represented graphically in this image, and they're actually surrounded by that red circle that just popped up. But it turns out that this could have happened. This was a great find. This was a good first step to determine, like, okay, this old Haumea could have been stable and it could have existed. And here are some of its characteristics. This is what it could have looked like, and this is a really good this was a really exciting find, actually, and just trying to find as many of these as possible to determine what that range of solutions could have been. So now we have to, we have the endpoint of what it is in the modern day. We have a good idea of what it could have been at the very beginning, but now we have to figure out what it looked like in the middle. And this is the part that gets a little bit tricky because we have to start taking into account the serpentinization and how that might have changed our answers. So at some point, the mass of Haumea needs to decrease from that slightly larger value to the modern day mass. But at the stage before the core grows via serpentinization, the core actually has to remain the same size. So all I'm doing in this step is smaller Haumea, slightly less massive Haumea that still has the same core size as that beginning solution, that one of the three solutions that I had on the other slide. So it's basically like the outside needs to change, but the inside needs to stay the same for right now. And it turns out there are a few solutions that overlap there when I was trying to model that middle Haumea. The larger mass Haumeas, the ones that were solutions on the previous slide, those are in yellow. Those are the yellow circles. And then the potential solutions for the modern mass Haumea with the similar or volume, those are in the blue squares. And there are some that overlap very well. There are others that you have to squint a little bit to see if they're close enough, but we included all of these because clearly there is overlap and there is enough agreement that we felt comfortable continuing with this idea. So now that we feel very confident in the geophysics, though, we need to talk about the geochemistry. So was serpentinization actually at work on Haumea? Did the process lower the core density from that more rocky to the more clay-like density? Was there even enough water available to hydrate the whole core, and could it have been done in the lifetime of the solar system? So for this step, we actually used a geochemical model called Icy Dwarf. This is a one-dimensional C code that is available on GitHub, and I actually put the code down on this screen because it was written by one of our collaborators, Mark Navu. He's a fellow Goddard person up here, and it does exactly what you might expect a geochemistry code to do. It studies the geochemistry of these planetary interiors. And we can use it here for Haumea to understand how the core changed over time, both in size and in terms of temperature and potentially composition, although we haven't done that part yet. We wanted specifically to study how much Haumea could have been hydrated at this step. So this is an example of what some of the output might look like. This is a temperature output, and what these beautiful colors in the middle here, the bright green and the dark blue, those represent the color contours for temperatures that liquid water could have been present, either with or without different things like ammonia to actually make it a little bit more liquid in this state. So it's different inclusions. That's what these colors represent. So when you see the next slide, just know that you're looking for the green and the blue. All right, so this is the actual output that we submitted to in this paper. We have in the top left the graph of the temperatures for Haumea, and we see that, yes, there is a lot of green and there's a lot of blue, and that's very interesting in what we're looking at here because it shows that, okay, liquid water could have been possible inside of Haumea. We also have in the bottom left the densities plot, and what was really encouraging about this plot is, oh look, our densities between geophysics and geochemistry codes actually match up. That's good agreement. You don't want to have one code, you don't want to have two different codes saying two different values. That's not encouraging. But again, here we have another form of agreement in terms of what we were looking for in Haumea. For the one on the top right, I want you to focus on this blue. It kind of looks like the head of an Egyptian statue to me, but that is a structure that actually represents a liquid water ocean on Haumea. That's what this graph is showing. Like there could have been, the temperatures were right and the densities were right. There could have been a liquid water ocean on Haumea. So this is what that timeline might have looked like. There was a collision, differentiation began. Very soon after that, because of all that heat that was produced in differentiation, an ocean formed, and it actually sustained an ocean for about 250 million years. It has since frozen out, and now it's just part of that very icy mantle that we think exists on Haumea, but this is where we could be right now. So these are the key takeaways here, that Haumea was able to create and sustain a liquid water ocean for about 250 million years, which makes Haumea perhaps the most distant ocean world yet known. Haumea's, well, except for the ones that are exoplanets. So I'll say the most distant ocean world known within the solar system. We also think that Haumea's core was fully hydrated, but there was a very small section of the inner core that became dehydrated towards the end of the day. So perhaps, or towards the modern day. So perhaps Haumea should actually be modeled as a 3-layer ellipsoidal body and not just a 2-layer one, and we can investigate that in future work. The densities of geochemical codes and the geophysical codes are matching up very well, so that's good agreement that this mass spinning off hypothesis that we propose is working. We've actually submitted this paper. It's currently in review at the Planetary Science Journal, and we hope that it is out and you can read about it in much more detail then, or please feel free to ask me questions at the end of the talk. So now that I've talked about this potential ocean world in our solar system, I want to talk a little bit about why we care and what the bigger picture is when it comes to studying objects like Haumea. So I got my PhD by studying Europa, which is the most classic example of an ocean world. It really is a beautiful body, and it's one of the most compelling astrobiological targets, specifically because it has this global subsurface ocean that it must be very energetic. It's full of salts, which could be nutrients for different organisms that might live there. There's a big question mark on whether or not Europa is not just habitable, but inhabited. But of course, we can't talk about ocean worlds without also considering that there are former ocean worlds in our solar system, most notably Venus, which will be studied very soon by the Da Vinci and Veritas NASA missions, and many other countries are also doing missions to Venus. But we also consider Mars as well, which has a lot of evidence that it used to have a lot more liquid water than it does today. Right now, most of its water is locked up in different polar caps or at the very tops of its very large mountains, aka volcanoes. So what we study, or what I find so compelling about Haumea, is that it pushes my own personal understanding of what an ocean world is, and therefore the limits of what a habitable planet could be. And one of the ways that we can talk about this is through talking about belatedly habitable planets. So something like Venus might have been habitable 3 billion years ago, but it clearly is not today. So habitable zones themselves, right, so I should define what a habitable zone is first. A habitable zone, in terms of exoplanetary or just planetary science, is a distance, it's a range of distances from a star where liquid water would be present and stable on the surface of an Earth-sized terrestrial planet. So for a hotter star, the habitable zone would be farther away. For a cooler star, it would actually be a lot closer in. But of course, the suns themselves are growing and changing, and sometimes are more energetic and sometimes less energetic depending on where they are in their own life cycles. And at the same time, we know that planets themselves like to migrate sometimes within the solar system. So we have this constant dance of not only are things happening within the planets themselves, but they're also being influenced by a lot of outside factors that overall influence and can control their habitability. So we can talk about planets that might have been habitable at some point or will be habitable in the future, but are not currently habitable. And this is just one of the ways that studying Haumea can help us understand what the limits of habitability are. Plus, there is just such a large number of exoplanets now known. It's up to, I think it might have actually crossed the 5,000 threshold within the past week, which is an enormous number of planets considering we have 8 in our own solar system, but we have many more data points if we look elsewhere. And one of the trickiest parts, though, of studying exoplanets is that there are some that we don't have good analogs for in our own planetary system. So some of these ocean worlds that exist in exoplanetary systems, we don't fully understand how they work, only because we can't quite imagine exactly what they look like and exactly how they might function. We can put some very good constraints on it based on things like the orbital period, which is proportional to the distance from the star. And we can also estimate things like the mass and radius of some of these planets, but otherwise, trying to figure out how these exoplanets work is actually a very new and difficult area of research. So it's through studying all of the objects in our solar system, not just the ones that not just the planets themselves, but every single object, dwarf planet, asteroid, moon, you name it. It's going to give us a lot more information to interpret what we see in terms of exoplanetary data. And that's exactly what people like Linnea Quick have been doing in their work. So in this example, they examined 53 different terrestrial exoplanets. They did put limits on how big these exoplanets could be. And they evaluated how active they would be based on estimates of what their radioactive heating would be and different tidal heating from gravity interactions with its host star, and actually found that all 53 of these planets should be either volcanically or cryovolcanically active, which is a pretty massive finding. Like every single one could be geologically active. That's incredible. And not only that, but up to a quarter of these planets could be potential ocean worlds, which includes the entire TRAPPIST-1 system, which is one of the more famous exoplanetary systems that we know of. So with the launch, and I can say this now, with the launch and successful deployment of the James Webb Space Telescope, we're going to look at a lot more exoplanets in much finer detail. And it's only one of many missions that will come out in the future. So I want us all to keep an open mind about what more we will discover, and how, even if it seems like a long shot, how to interpret all of the data that comes our way. So with that, this is actually the last slide of my presentation. I will leave up my key takeaways. My email is there if you have any further questions that we don't get to today. But for now, I'm happy to take your questions.